Class, these are our informal geometry notes. We're starting chapter 8, so this is our first section, 8.1. We are learning about classifying polygons. So some of this will be review. Remember, convex or concave? Concave was when this shape looked like it was being caved in. And so that would be like this part here. Like if I draw a line from this side, I'm over here, you can clearly see that we've got this cave that goes in. So I'm going to call that concave. This one doesn't have any cave-ins, right? Like if I draw a line and extend it from a side, it doesn't go inside the shape. So here, when I drew that line, it went inside the shape. Here, it does not. So this is going to be convex. You kind of need to see that both of them to see the difference. Again, same thing on this one. It's convex. And a star is definitely concave. So just because it's a shape we recognize doesn't mean it's not concave. So this we did before in an earlier chapter. I think you're going to understand that. So equilateral polygons, we've talked about that. Equilateral means we have all equal sides. So we're just kind of reviewing some vocabulary right now. Equiangular means we have all equal angles. And so if you look at some of our shapes here, this one with all four sides equal, but we don't really know anything about the angles, that's going to be a rhombus. I just think it's good to go back and connect to vocab from earlier chapters. If we have all equal sides on a triangle, it's actually going to also have all equal angles, and it's going to be an equilateral triangle, right? Equilateral triangle. With a triangle, those two things go together. On this one, we have four equal angles, but we don't know anything about sides, and they don't look equal. This is actually just a rectangle. And for the last one, of course, we have an equilateral triangle again. And I'm going to go ahead and put those marks on each angle that show that they're congruent. So for regular polygons, this is a new word now. A regular polygon is a polygon where, if you notice on all these diagrams, look at my angles are all marked equal on this one. They're marked equal on this one and this one on this one. But my sides are also congruent. So this means we have all equal sides and angles. So that's what a regular polygon is. Okay, so now we're going to do a little bit further classification. We want to determine whether the polygon is concave or convex. So that's like what we did at the beginning, and then whether or not it is regular. So remember, regular means we have to have equal sides and equal angles. So first, is this convex or concave? So it's definitely convex. Next one is caved in, so we're going to write concave. And again, if I draw a line on this side, it ends up going through my shape. Last one again is going to be convex. And then we want to look at whether or not it's regular. So are all the sides and all the angles equal? So are all my sides are equal? So sides, check. How about my angles? Are all my angles equal? Well, these two are equal and these two are equal. So they are not all equal. So it is not going to be regular. But because all of my sides are equal, it is equilateral. I'll put that in parentheses, but it is equilateral, and that's a little bit messy. I kind of snuck that word in there. So it was not regular because our sides were congruent, but our angles were not. Okay. On the next one, if it's concave, we're not going to have all sides and angles equal anyway, but we do have all equal sides on this. So it's going to be not regular, but again, it is equilateral. But it is equilateral. Always lots of vocab and geometry. So the last one, let's take a look. All four sides are congruent and all four angles have that little box to show that it is a right angle. So those are all equal. And so because our sides are congruent and our angles are congruent, we're going to say that it is regular. And specifically, it's a square, right? That's the name for that. I guess I should have written something here. Sides congruent, angles not. So that's what we're checking when we look for regular. So let's go ahead and go to the back of our notes. We've got more vocab. A lot of this is going to be easy for you. You probably remember that 3 sides means it's a triangle, and 4 sides means quadrilateral. So these are polygons with a number of shape. And we did this in an earlier chapter also. If there are 5 sides, that's a pentagon. And you might not remember this word off the top of your head, but then it should be familiar when I write it down. So pentagon shouldn't be a brand new word. If it has 6 sides, it's a hexagon. 7 is a heptagon. These lines are pretty small. 8 is an octagon. 9 is a nonagon. And 10 is a decagon. Now 11's kind of a distractor here. So remember before when we talked about like weird numbers of sides and we didn't have a name for it? Well, that's what 11 is. So we just call it an 11gon. So there's going to be lots of them past 12 where we don't have a special name. And so that's what you would just do. If it had 37 sides, it'd be a 37gon. But we do have a special name for 12, and that's dodecagon. Remember, you can use in informal geometry your notes on tests and quizzes. So, I mean, we should probably know a lot of these. I would imagine you know at least up to 8. But you can look back at your notes. So make sure you can find them. So we're doing a little bit of algebra review because we're going to be using these ideas about simplifying square roots in some of our math problems. So we are simplifying radicals. So the basic idea behind this, kind of what we're doing is we're breaking down the way a radical looks so that the number inside it is not so big. So these are all square roots we're working with right now. So radical is the symbol, but they're really square roots, but we're not putting the square there. So really quickly, let's just think about like the square root of 25. Well, 25 is 5 squared. And then a square root and a square cancel each other out. That would just be equal to a 5. And remember, 5 times 5 does make 25. So if you're looking at a square root, it's like what number times itself or what number squared would give you that number. So because 5 times 5 makes 25, I can write it as 5 squared, which means it's just a 5. So that's kind of this property that we're going to be using to simplify square roots. So I like to use a factor tree. You might have used a different method in your math class last year, but I like that this is a method where you don't have to be terribly good at multiplying and dividing. You just have to be able to break stuff down. So I'm going to just go over here and say, well, what is 12? What multiplies to make 12? Well, 2 and 6. And then what multiplies to make 6? Okay, 6 would be 2 times 3. Once I hit a 2, right, I can't break it down any further without using 1. 1 is not terribly helpful. If we were using 1, we could keep going on and on forever. So now all of these numbers at the end, those are the factors, the prime factors of 12. So what I notice is I have 2 of these 2's and I have 1 3. So I'm going to take 12 and I'm going to write it as 2 squared times 3. And on the first problem, we're going to do lots of work. I'm going to have my square root over this entire thing. And then it turns out that I can break a square root up. I'm not using math terms here, over multiplication. So I can write this as square root of 2 squared times square root of 3. And we know from looking at this property above and kind of thinking about how square roots work that if I have a square and a root, those are going to undo each other. They are inverse operations. So this is just going to be a 2. So now I have 2 times the square root of 3, and we're going to write that as 2 roots of 3, just like this. So sometimes people say 2 square roots of 3, sometimes they say 2 radical 3. There's a lot of different ways that you can say that. And if you have a different way, just let your teacher know. It's probably just fine. So it kind of depends on the teacher and the class. So again, all we did was we took this number, we broke it down into its prime factors. Prime because 3 doesn't have any more factors, right? Unless I use 1. So I'm stuck. And then we looked for ones that we had pairs of because we could take square roots. All right, so this one is all set. And you can see where it's simplified, right? Instead of having a square root of 12 here, now I only have a square root of 3. It's a much smaller number. That's what we mean when we say simplified. Next one is 63. So 63 is 7 times 9. 7 is done, right? I can only do 1 times 7, so I don't do any more factoring for that one. But 9 is a 3 times 3. So here's my two factors. I have a 3 times 3, so 3 squared, and I have a 7. So I'm going to jump up here, and 63 I can write as the square root of 3 squared times 7. So that's going to be the square root of 3 squared times the square root of 7. Square root of 3 squared is just a 3. And so we have 3 square roots of 7. We're going to look at shortcutting our math work on the next one. So 44, let's go ahead and break that down. All I can think of right away is 4 times 11, and 4 is 2 times 2. So here's our two things that we need, right? 2 times 2 will make a 2 squared. That's what we're looking for. And we also have an 11. So let's write this as square root of 2 squared times the square root of 11. So notice this time I'm breaking it up into the square roots right away because I know I can do that. I'm not even putting the times sign. So I am shortcutting that work a little bit. And then the square root and the square here are inverse operations. So we're just left with 2. So 2 roots of 11, 2 square roots of 11. Okay, 75. So I'm going to do what many of my students would do, or many of you will do, and just say, well, it ends in 5. I know I can divide it by 5 and go from there. So let's see, 5, and then this would be 15. So 5 times 15 makes 75. So you might have to grab a calculator. And then 15 is 5 times 3. So I have a 5 and a 5 and a 3. So the two factors of 5 means I can write this as the square root of 5 squared times the square root of the 3. I'm always trying to put my squared factor first because I do want that whole number to be in front of the radical sign. So the square root of 5 squared is just a 5. Square root of 3, we'll say square root of 3. All right, let's go to our bottom row. Let's see, 27. All right, so for 27, let's see, 27 is 9 times 3, and 9 is 3 times 3. So this one's interesting because I have 3 factors, but really I need 2, right? I need something that's squared because a square root will undo a square. So I'm going to write this as a 3 squared and then another square root of 3. So this one will have to stay inside the jail. You've got to have a square in order for the square root to undo it. So if I have a square root of a square, I just have a 3. So this is going to be 3 radical 3. 80 is a bigger number. I feel like that one's going to be trickier. So let's see what we got. I know 80 is 8 times 10. That's the easiest one that comes to mind. 8 is 2 times 4. 4 is 2 times 2. And then 10 is 2 times 5. Wow. So when we look at our prime factors are all the ends of these branches. So the 2 and the 2 and the 2 and the 2 and the 5. So this is really interesting because I have 2 factors of 2 and then I have 2 more factors of 2. So let's see how we write this one out. So I'm going to write that 80 is a 2 squared. So square root of 2 squared. I have another square root of 2 squared. So that's these two 2's and then these two 2's. But then I'm also left with a 5. So I'm going to write down square root of 5. And then my square root and square would just make a whole 2. And then this one's going to make another whole 2. Remember, we're multiplying in between these because these guys multiplied together and made 80. So this is going to give me another factor of 2. And then I have a square root of 5. So 2 times 2 makes 4 radical 5. All right, on the last one, 180. Oh, goodness. Now we really are going to have to do a factor tree. Okay, so 180, it ends in 0, so 18 times 10, right? That's an easy way to split this up. 18 would be 6 times 3. 6 would be 2 times 3. And let's see, 10 is going to be 2 times 5. So the ends of my branches, 6 isn't the end of a branch because I have more branches coming from it, are 2 and 3 and 3 and 2 and 5. So do we have anything that we can write squared? Well, we have the 2 2's here. So I'm going to write down a 2 squared. We have 2 3's, so I can write down a 3 squared. And then we also have this 5. So we've got square root of 2 squared, square root of 3 squared, square root of 5. And remember, these are all being multiplied because 2 squared times 3 squared times 5, those numbers multiply to make 180. So squares and roots will inverse each other. So this is just going to be a 2 times, this one's going to be 3, and then we have square root of 5. And 2 times 3 is 6. So 6 radical 5. So hopefully this jogged your memory. I know that you've done this in a math class before. I do think this is going to be an easier method for everyone, but if you have a different method that you understand for simplifying radicals, you're welcome to do that as well. Just talk to me. So make sure that you are asking questions in class.